Okay, so let's continue with our similarity theorems. So we have here the third one, SSS Similarity Theorem. If the corresponding sides of two triangles are proportional, then the triangles are similar. So you want to prove that triangle RGA, okay, is similar. Okay, so the symbol for similarity again is this one, or it can be this one. Okay, so triangle RGA is similar to triangle QDN, and the ratio of their sides RG all over QD is equal to GA all over DN is equal to RA all over QN. So for this one, guys, the first thing that we have to do is we have to construct. Okay, we have to construct first this line in order to solve for the proportion that we have here. So let M and O be points on RG and RA respectively, such that RM is equal to QD and RO is equal to QN. So we have here so this triangle right here is going to be congruent to this one. But that's the idea, okay? The reason is a line segment can be constructed congruently on a given segment. So it's division of congruent segments. So construct MO, and MO must be equal to DN. So 2 points, two distinct points, the terminal line. And it's also given, okay, so it's also given that RG all over QD is equal to GA all over DN is equal to RA all over QN. So the ratio of the sides of the three triangles, okay, so RG, okay, QD, GA and DN, and RA and QN are congruent. So RG over RM is equal to, okay, RG over RM is equal to RA all over RO. So that's substitution property of equality, right? Okay, since we said here that MO is equal to DN. Okay, so there you go. And angle R is also congruent to angle R. Okay, so this reflects the property of congruence. Triangle RMO. Okay, triangle RMO is similar to triangle RGA using the SAS Similarity Postulate. Okay, so we have here a side, an included angle, and another side that are congruent to each other. That are proportional, the sides are proportional to each other. Okay, so then we have MO all over GA. Okay, MO all over GA is equal to RM. Okay, RM all over RG. Okay, so that's going to be definition of similar triangles. Since we have here a similar we have here these similar sides of similar triangles. Then we can say that MO all over, okay, MO all over GA is equal to QD, okay, QD all over RG. Since RM is equal to, okay, RM is equal to QD. Okay, so there you go, substitution property of equality. And if we use the multiplication property of equality, MO is going to be equal to GA, okay, multiplied by QD all over RG, and DN is going to be equal to GA times QD all over RG. Okay, and therefore we have here triangles RMO and the QDN are congruent to each other by using the SSS triangle congruence postulate, and therefore since they are congruent, we can also say that the two triangles are similar. There you go, good job, to each other. Okay, so let's try to prove the SAS triangle triangle similarity theorem. Okay, if in two triangles, two pairs of corresponding sides are proportional and the included angles are congruent, then the two triangles are said to be similar. So we have here triangle IOU and triangle ACE, and we have here OI. Okay, OI over CA is equal to OU over CE, and angle O is congruent to angle C. We want to prove that triangles IOU and ACE are similar. Okay, are similar to each other. So as with the SSS triangle similarity theorem, what we're going to do to this one is we're also going to construct a segment. Okay, so let G and R be points on OI and OU respectively, such that OG is equal to CA and OR is equal to CE. Okay, so a line segment can be constructed congruently to a given segment. And then we constructed here GR. Okay, 2 points determine a line. Angle O is congruent to angle C, so that's a given. Therefore, using the SAS Triangle Congruence Postulate, we can say the triangles GOR and ACE are congruent to each other. And we can also say that OI all over CA, okay, OI all over CA is equal to OU all over CE, okay, by using, okay, so that's a given, okay, and therefore OI all over OG, okay, is equal to OU all over OR. So since CA is equal to OG and CE is equal to OR, we can say that using the substitution property of equality, this is valid. And GR is parallel to IU, so that's the converse of the basic proportionality theorem. Therefore, we can say that angle OGR, okay, is congruent to angle OIU. So if two parallel lines are cut by a transversal, okay, so the transversal here being this one, and these are two parallel lines, then, okay, then their corresponding angles, okay, so these angles, these corresponding angles are congruent to each other. And by using the reflexive property of congruence, we can say that angle O is congruent to angle O, and therefore we can say by using the AA similarity postulate that triangle IOU, okay, so let's clear this up. So triangle IOU, okay, IOU is congruent to triangle GOR using the AA. Okay, so this angle, they share that angle, and also this angle, and then this angle. So they are similar to each other. And also we can say, we can extend that definition that triangle IOU is also similar to triangle ACE, okay, from statement 4 as well, by using, okay, so by statement 4 using the transitive property of equality. Okay, there you go. Okay, so for the second word word problems for triangle similarity theorem, so let's try to explore some word problems involving triangle similarities. Okay, so for number 1, we have here Severus wants to create a floor pattern in his house using the flip symbol of the omnitrix in Ben 10, but in his own version. The triangles are similar but not congruent to each other. He measured at the sides of the triangle and drew a blueprint given on the right, so determine whether the triangles are truly similar to each other. Okay, so how do we know, how do we do that? How do we know whether the triangles are truly similar to each other? And how can we find the measurement of TO? Okay, so using the triangle similarity theorem, okay, we can say that since the two triangles are similar to each other, okay, so since triangle ISH and triangle TSO, okay, so they're similar to each other. So this can be the symbol for similarity, or this one up. Okay, so let's try to use this one since it's much easier to use this one. So ISH is similar to triangle TSO. So therefore their corresponding sides must be proportional. So that means IS all over SO is equal to HS all over ST. Okay, so what's the measurement of IS? So IS is equal to 12, and SO is equal to 18, and HS is equal to 16, and ST is equal to 24. Okay, so we can find the lowest value, or the lowest term of 12 over 18. So we can divide that by 6, you're going to get 2/3. And this one, if we divide this by 8, we're also going to get 2/3. So therefore this one proves, okay, this proves that the side measurements of the two triangles ISH and TSO are proportional to each other. So how can we get the value of TO? Since we have here IH, okay, so IH measures 10 centimeters, therefore we can say that IH all over TO is equal to 2/3. Is that right? Because this is the proportion that we got from the sides. And therefore we can say here, okay, so let's move forward here. So since the value of H is equal to 10 all over TO, so this is going to be 2/3, right? And this becomes 30 is equal to 2 times TO, and therefore TO is equal to 15 centimeters. Okay, so that's how easy we can get the value of TO. Okay, so we have this second problem. Reynaldo placed a mirror on the ground on the base of the floor of a fountain and mark it 50 feet from the floor fountain. He walked backwards until he saw the top of the fountain and the middle of the mirror. At that point, Reynaldo's eyes were 5.5 feet from the ground and he is 8 feet from the image of the mirror. Given that angle A and angle E are right angles, so use similar triangles to find the height of the floor of the fountain to height of the floor fountain in market. So we want to find x here. Okay, so how can we get this one? How can we get the value of x? So by using similar triangles, we can solve this problem. Okay, since we have two right triangles here, we have here triangle. Okay, we have here triangle CAP. Okay, triangle CAP is similar to triangle REP. Okay, so they are similar to each other. Since the two triangles are similar, therefore we can say that their side measurements, okay, so the side measurements are proportional to each other. So therefore we can say that CA all over RE is going to be equal to AP all over PE. Now we don't know the value of RE, so we're going to write that as x, right? But we do know the value of CA, so it's going to be 5.5 all over x is going to be equal to 8 all over 50. Okay, and from here, guys, we can use cross multiplication. So this gives you 8x is equal to 50 times 5. And what's 50 times 5.5? Sorry, 50 times 5.5 is 275. Okay, so 8x is equal to 275. If we divide both sides by 8, okay, so therefore the value of x is going to be equal to 34.375 or 34.38 feet. Okay, so therefore that's the height of the fountain that we have here on market. Okay, so enrichment. Okay, so for enrichment activity, we're going to be discussing similarity theorems about right triangles. Okay, so in a right triangle, the altitude to the hypotenuse yields 3 similar triangles, and for the second one, the altitude to the hypotenuse of a right triangle divides the triangle into 2 triangles that are similar to the original triangle and to each other, and there follows 2 corollaries. Okay, so the first one is the length of the altitude of the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse, and the altitude of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean. Okay, so we're getting the geometric mean now. The geometric mean is equal to, again, B is equal to the square root of 8 times C, where A and C are the legs. Okay, the legs, okay. These are the legs of the triangle. Okay, and of the length of the adjacent hypotenuse segment and the length of the hypotenuse. Alright, so let's check the proof for theorems 1 and 2. Given right triangle ACB and CD as the altitude of the hypotenuse, we have to prove that triangle ABC is similar to triangle ACD. Okay, it's also similar to triangle CBD. So these 3 right triangles that we have here, these 3 right triangles should be similar to each other. So given right triangle ABC with CD as the altitude of the hypotenuse, both smaller triangles on the illustration on the right are right triangles as well. So each triangle, okay, so we have here 2 right triangles, 2 right triangles. So we have here ACD and triangle BCD. Okay, so each triangle also shares an angle with angle ABC. Therefore, by using the AA, okay, using the AA similarity postulate, it can be said that triangle ACD and CBD, okay, are similar to each other. Okay, since both smaller triangles are similar to triangle ABC, therefore their corresponding angles must be congruent, and hence the 3 triangles are similar to each other. Triangle ABC ACD and CBD are similar to each other.